Now that we've defined the Pythagorean theorem and we know how to use it, we can move on to defining and learning how to use trigonometric functions. These functions are important because they give us a relationship not only between the sides, but they give us a relationship between the sides and the angles of a right angle triangle, and they will allow us to solve for one or two sides when we only know the hypotenuse and one of the angles. So let's start by making some definitions. And for now, just take these to be definitions. That's all they are. First of all, we know that there are three angles, of course, in a right angle triangle. And we know that this angle here is 90 degrees. We're going to define these other two angles here by two Greek letters, theta and phi. This is sort of a standard definition. And we have still the three sides A, B, and C. And because the sum of the angles inside of a triangle is 180 degrees, we can write the following. We can say that theta plus phi plus 90 degrees is equal to 180. And then by subtracting 90 degrees from both sides, this tells us right away that the sum of the two angles, which we called theta and phi, has to be equal to 90. This is also useful in itself because if we know one of the two angles, we automatically know what the other angle should be. And the trigonometric functions are three functions that are defined as ratios of the two legs and the hypotenuse. They're defined in the following way. Let's consider the angle theta, which is the angle between the hypotenuse and the horizontal side A. The cosine, written by cos, of the angle theta is defined to be the ratio of A over C. The sine of the angle theta, which is B over C, so it's the opposite side over the hypotenuse. And then we have the tangent, which is the side B divided by the side A. Now you might say, what are these three? As I said, for now, just take them to be three definitions of three functions that we will see in a second how to use. Before we do anything else, let's look at the third one here, the tangent. We can actually define the tangent in terms of the sine and cosine in the following way. If I divide the numerator and denominator by c, I'm still not changing the value of the function because I'm dividing both numbers by the same number. And from algebra, you know that that doesn't change anything. But now we see that b over c, which is the numerator, is the sine. And a over c, which is the denominator, is actually the cosine. So there's a nice relationship between tangent, sine, and cosine, which tells us that if we know the sine and cosine, we automatically know the tangent. Now we can also relate these three functions to the three trigonometric functions that we could define by using the angle phi. Notice that the cosine of the angle theta was defined being the angle between C and A is defined as the ratio of A over C. And the sine of the angle theta was defined as the ratio of the opposite side, B, divided by C. We could have done exactly the same thing using phi, this symbol here, and we would have said that the cosine of phi is equal to the angle, phi is the angle between B and C. So in the same way, the cosine of phi should be the side B divided by C. And the sine of the angle phi should be the opposite side, which is A, divided by C. And clearly, the tangent is still the same identity holds, so the tangent will be the sine of phi divided by the cosine of phi. But now there's a nice relationship between the three trigonometric functions that we defined in terms of the angle theta to the three trigonometric functions that we define in terms of the angle phi. Now notice here that the cosine of theta is a over c, but that is the sine of phi. Likewise, the sine of theta is b over c, which is the same as the cosine of phi. So we can say right away that depending on which angle we use, the sine and cosine are switched. What do I mean by that? I mean that the cosine of theta is equal to the sine of phi, and the sine of theta is equal to the cosine of phi. And these relationships always hold regardless of what the values of the angles are. Now, you might not see the utility of these functions yet, but we'll see in a minute how they allow us to express the legs in terms of the hypotenuse in one of the angles, and therefore they will allow us to solve the right angle triangle completely just by knowing the hypotenuse in one of the two angles. Before we do that, let's do an example by actually plugging in the numbers and seeing how you would do that. Okay, let's say that we have a certain right angle triangle, which is like this, and we're given that the two legs here are 8.71 and 3.66. As you know, I don't like to use very simple numbers. I think that's very bad practice, because then in reality when you solve problems you don't get numbers that are nice whole integers like 3, 4, and 5. So I would rather do it with real numbers, with decimals from the start. We want to determine what the sine, cosine, and tangent of the angle that we call theta, therefore the angle that subtends the horizontal side, are. And in order to do that, if we go back to our definitions, we also need to know the hypotenuse. We yet don't know what the hypotenuse is in this case, but we know the Pythagorean theorem. We know that the hypotenuse c is equal to the square root of a squared plus b squared. And we know that a, in this case, is this number here, and b is this number here. And therefore we can just plug in the numbers and obtain what c is. So we first of all do that. I'm going to do the hard work for you, but as always, I would suggest you pause the video and attempt the problem yourself to make sure that you understand the concepts. In this case, if you plug in the numbers, clearly using your calculator, you will get a hypotenuse rounded of 9.45. So we also know this one here. Okay, now that we know this, we can solve for the sine, cosine, and tangent. And you might ask yourself, how do I know how to calculate these things? Well, generally you just use your calculator. Your calculator also has these functions in it, so you don't need to do any manual work. In this case, you just have to calculate ratios, which is even easier. So let's start with the sine of the angle theta. The sine is the opposite, so the side B, opposite to that angle, divided by the hypotenuse C. This is 3.66 divided by 9.45. Again, you plug this into your calculator and you get 0.39. For the cosine, let's do it down here. It will be A divided by C, which is 8.71 divided by 9.45. And again, plugging in the numbers, you will get 0.92. Lastly, we have to calculate the tangent. And the tangent, there are two ways of calculating it. Either we can take these two numbers that we just calculated and take the ratio of those two numbers, because we know the sine and cosine. So we can go ahead and do that and do 0.39 divided by 0.92, and you can verify that this is rounded 0.42. Or likewise, you can use the fact that the tangent is b over a, and I'm going to let you verify that rounded you get more or less the same answer. So the two answers agree as they should. Now, I'm pretty sure that you still don't see the utility of all of this. You might say, why are we complicating things? We had a Pythagorean theorem that tells us everything we need to know about the triangle. Why do we need to do this? Well, the reason why we need to do this is because sometimes the only thing we know in a triangle is the hypotenuse and one of the angles. And we would like to be able, from this, to extrapolate what these two sides are, A and B, and perhaps maybe the angle phi, but that's generally not the case. So, can these functions help us determine what A and B are if we don't know? And the answer is yes. How? Well, we know now that if I take the ratio A over C, that gives me the cosine of the angle theta. So what can I do here? Well, I can solve for A if I know C and the angle. I can multiply both sides here by C. On the left, I'm multiplying and dividing by C, so that cancels. And that tells me that the side A, the horizontal side, is equal to the hypotenuse C times the cosine of the angle. And in the same way, I know that the sine of the angle is given by B over C. I can do exactly the same thing here. I can multiply both sides by C. The C cancels on the left, and that tells me that B is equal to the hypotenuse times the sine. These two are two very powerful definitions. Especially when we deal with vectors, these two will allow us to find what are known as the components of the vector, which are nothing more but the legs of a right angle triangle. And also, I could find from the tangent, if I know one of the sides, let's say I know A, but I don't know B, I could do the same thing. I could multiply both sides by A here. And that tells me that if I know A and I know the angle, then the side B will be equal to A times the tangent of the angle. This third one is less used than the previous two, but it's important nonetheless. This also gives us a very important relationship between the sine and cosine of an angle, which is always true, and is known as the Pythagorean identity, and it is related to the Pythagorean theorem. So before we do another example, let's see how that identity comes about. What we know about angles and triangles is the following now. We have these three sides here, and we know clearly that C is equal to the square root of A squared plus B squared, or alternatively, if you want to write it like this, C squared is equal to A squared plus B squared. We also know now that A, if we know this angle here theta, A is equal to the hypotenuse times the cosine of the angle, and B is equal to the hypotenuse times the sine of the angle. What happens if we combine these two pieces of knowledge here the fact that we know the sides in terms of the angle, and the fact that we know the Pythagorean theorem. Are these two things related? And do they tell us anything more about the angles? Well, let's see. One thing we can do is we can take these definitions for A and B in terms of C and the cosine and sine and just plug them into the Pythagorean theorem and see what we obtain. So we have C squared is equal to A squared. For A squared, I'm going to plug C times the cosine squared plus B squared, for which I'm going to plug C times the sine squared. I can simplify, and I can say that C squared is equal to C squared on the right times the cosine squared of theta plus C squared times the sine squared of theta. But the C is common to all of them, so I can actually divide both sides by C squared. Dividing the left here gives me 1. These also give me 1. And so I come to this very important identity, which tells me that 1 is equal to cosine of theta squared plus sine of theta squared. Notice that this is true for any angle whatsoever. I did not make any claim about what the angle is. I just defined theta to be an angle, and the equation followed from that. So this is a very powerful identity in itself, and it's known as the Pythagorean identity, or at least that's the name I know it by. And as you can see, Pythagoras got a lot of credit for the work he did with right angle triangles. Let us now do an example with this, and then in the next videos we'll put everything together in dealing with vectors. Let's say we have a right angle triangle, and this right angle triangle has a hypotenuse of 7 meters and an angle theta, which we always define to be the angle with the horizontal side, to be 36.9 degrees. We want to find the length of the two sides. In this problem here, you need your calculator. One thing that I can tell you is to make sure that your calculator be in degrees, because if you have it in radians, you're going to get an answer that is incorrect. Let's start as usual by drawing our right angle triangle. That always helps, drawing a picture. This is our theta, this is our C, which we know to be 7 meters, and we want to determine what A and B are. Now, we just learned that if we know one of the angles and you know the hypotenuse, you can determine the other two sides by the following. A is equal to the hypotenuse times the cosine of the angle, and this for our case will be 7 meters times the cosine of 36.9 degrees. This is the time when you plug it into your calculator. Your calculator has sine and cosine, so you just hit cosine on your calculator, put in 36.9, make sure this is in degrees, multiply by 7, and round it, you get 5.60 meters. In the same way, to find B, you do the same operation, but you have the sine instead of the cosine. So it will be 7 meters times the sine of 36.9 degrees. And again, round it, you get 4.20 meters. It would be nice if we can sort of check our answer. And one way to check our answer is if we know what A and B are, then A and B squared, added up, and square root it. In other words, using the Pythagorean theorem, should give us C. So let's verify that. That's a nice exercise. A is 5.6. So we square that. B is 4.2. We square that as well. We add them and we take the square root. If you do this in your calculator, you get 49.02 meters squared, square root it. The square root of 49.02 is very close to 7. The only reason why they're not identical is because I rounded these two numbers in my answers, but you can see that up to rounding, this gives you indeed the hypotenuse that we started with. So when you do these problems, if you're not sure about your answer, one way of checking that you got the correct numbers is to plug your answers for the legs back into the Pythagorean theorem, and they should give you back the hypotenuse that you started with. In the next few videos, we're going to apply all of this machinery to the study of vectors.